So today's class we're going to be doing some new material. So last week we were talking about vectors. We're actually going to be getting into a subset of vectors, and those are what are called one-dimensional vectors, so something that moves in one dimension. Next week we're going to be talking about things that move in two dimensions, so projectiles, like something falling off a table or a cannonball being launched. But we're going to be starting today just with one-dimensional kinematics. And so when we look at the word kinematics, it's from a Greek root actually. So what do you think kinematics means, or where do you think it comes from? Shares common roots with kinesiology, kinesthetics. What do those two words kind of mean? So movement's thematics, so we're studying the motion of bodies, right? Kind means body, so kinesthetics and kinesiology, those are involving motion of bodies. And so when we're looking at definitions in kinematics, there are two kind of root definitions that we need to look at. The first is what's called the velocity. And the velocity in the language of calculus, if you've seen it before, is the time derivative of the position. But we can also say without calculus that if we want to find some average velocity, so some average velocity, this is equal to the ratio of a change in distance over some change in time. Okay, where x is denoting the position, sorry, delta x over x. Delta x over delta x. This is delta x over delta t. Okay. You guys, feel free to correct me if I make mistakes, because if you don't, then this is going to be on the internet forever, to my shame anyway. So the average velocity is defined to be the change in position over the change in time. We can also define the average acceleration in a very similar way, and that's to say the average acceleration is going to be the change in velocity over some change in time. Okay? And like I said, if you're familiar with calculus, you can write these in terms of derivatives. Now, some other things that we can say about velocity and acceleration is these quantities can be positive or negative depending on how we're defining a coordinate system. And that tells us, for instance, if something's moving away from you or it's moving towards you, or if something's speeding up or it's slowing down. So in the case of displacement or position, we say that a positive displacement conventionally, when we define some coordinate system, is going to be to the right, so this would be the positive direction, and to the left would be the negative direction. We could also say this in some vertical coordinate frame, this could be up or down. Okay? But you're also free to change these around, but you just have to make sure that you're careful in defining some coordinate axis when you're doing this. But conventionally, this is the coordinate axis that we use. In terms of the velocity, if something has a positive velocity and a positive acceleration, that means that it's speeding up. If it has a negative velocity and negative velocity, it's also speeding up. So what that tells you is that the velocity is increasing, but it's increasing in the same direction that it's already moving. And you can see, if you think about the converse, that you could have a situation where you have a positive velocity and a negative acceleration. So for instance, if I throw a ball up in the air, it has some positive velocity if I say up is positive, but that velocity is decreasing as it goes to the top. So that's an example of a positive velocity and a negative acceleration. That's slowing down. A negative velocity and a positive acceleration is also slowing down, just kind of in the opposite direction. And then you can have a couple of different combinations where you have zero acceleration or zero velocity. So in the case that you have some positive or negative initial velocity and zero acceleration, this is just going to be something that's moving with some constant velocity. And you can see that from this equation right here for our average acceleration. If our average acceleration is going to be zero, then our change in velocity is also zero. And if the change in velocity is zero, that means that you have the same velocity for all times. Okay. Now finally, we could say that if something has a zero velocity and a positive or negative acceleration, that means it starts from rest. So for instance, if I had this piece of chalk and I let it go, it has a zero velocity when I let go of it, but it has some acceleration, so the velocity is going to change. Okay. All right. So I'll get to our first clicker question. So a lot of what we're going to be doing today is to build off of these ideas of the relationship between position, velocity, and acceleration in order to evaluate plots and create plots. And so this question asks us to construct the plots or the graphs of the position, velocity, and acceleration for a car that's traveling at constant velocity minus v. And you can click in F when you're finished. Okay, so take a couple of minutes to work on this one. All right, so let's go ahead and talk about this one. And what I'd like to do first is to do just a really brief review of the equation of lines, in particular the equation of straight lines, to connect this to some of the things that we're talking about here. So you'll remember from high school or maybe middle school that when you had some axis like this, where I have some y and some x here, that if I had some line like this that goes this way, then the equation of this line is what we can write in what's called the slope formula form. And don't ask me why they call this M and B. People come up with weird names for things. But we can kind of pick off what these terms mean. So y is really the function of x that we're plotting here. What is m? M's the slope, right? How do we define the slope? Rise over run, which is the change, somebody said over here, change in y divided by the change in x, right? And b is the y-intercept, okay? Now, let's kind of take this and work with it in terms of the kinematics that we're learning right now. So, what would this equation look like if instead of having my y and my x here, if I had some x as a function of time on the vertical axis and time on this axis? How does this equation change? Well, what I can do is I can say that x as a function of time is going to be equal to the slope, m, times the variable on this axis, the horizontal axis, which in the first case was x, in this case it's t, plus the y, or in this case the x of t intercept. We're not particularly interested in this, but I can say that this is some like initial position, x0. So then what we can do is we can say, okay, for these variables, how can I write the slope? Well, the slope is just going to be equal to the change in this variable, right? The change in this variable divided by the change in this variable, right? And so what that means is that the slope here is really delta x divided by delta t. Well, what is delta x divided by delta t?
Average velocity.
It's average velocity, right? And so what that tells us is when we're plotting the position versus time, that the slope of this plot should be our velocity. So this is x, the position is a function of time, and this is time. So for this particular example, now that we know that the slope of this line should be our velocity, what should the slope of this line look like? It's negative. It's just a line that slopes down here. And so if we start from the origin, we didn't say here specifically if I start displaced from the origin or not, but we'll assume that we're starting from the origin. This is what the position versus time looks like. Now let's plot what the velocity versus time looks like. So this is v of t, and this is t. So how should this one look? You guys tell me. I don't know.
Straight.
It's just a straight line, right? And it's constant, just like that. Is this okay? It's wrong. What's wrong with it? It should be negative. It should be negative, right? Because we know this velocity is negative. And there needs to be some correspondence between these two plots. So this plot having a negative slope is telling me that this line needs to be negative here, right? These have to, they have to talk to each other, okay? Now, the last plot is going to be our acceleration. And again, there's kind of two ways that we can look at this. So this is the acceleration as a function of time. This is time. What should this one look like? 0, right? Why?
It's the slope of the velocity graph.
Right, it's the slope of the velocity graph, and we can see that here, right? So this equation is telling me that the velocity is the slope of the position graph. This equation is telling me that the velocity is the slope of the acceleration graph. And so we see in this set of plots that we have here, this one has a slope of 0, and that tells me that the acceleration is 0. What's another way that we could come to this conclusion, aside from the plots and aside from talking about the slope? Has something to do with a very particular word in here. Constant, right? So if I have constant velocity, that means the velocity is not changing. If the velocity is not changing, there's no acceleration. Okay? Good. So we got another one of these. Okay. So now what we want to do is we want to do another one of these plots where we say that we have a car that starts at a stoplight and then speeds up. And we want to plot the position, velocity, and acceleration for the car. Okay? So go ahead and take a minute to talk about this one. Okay, so let's talk about this one. So in this case, we say that we have some car that's accelerating from rest at a stoplight. And so we can start kind of in the middle here because we know something about the velocity, right? We start from rest. So what does it mean to start from rest? 0, you're not moving yet. And then the velocity is going to increase. So what would that look like?
The line goes diagonal.
Yeah, it would be a diagonal line like this, right? And it's positive, right? Because velocity is increasing. Velocity is not decreasing, okay? So now we have this plot, blowing a chunk of hair at me. We have this plot. So we want to do our acceleration plot. So how is the acceleration related to the velocity? It's the slope of the line, right? So does the slope change? No, it doesn't. So what that says then is I should have just some horizontal line for our acceleration where it's going to be a positive line because this is a positive slope. Okay. Now let's look at our position plot. So for our position plot, we know that the position, at any point, the slope of the position is going to be the value of the acceleration at that point. Okay? So when I start, my velocity is 0, which means that the slope of the position plot should be 0. So I have something that looks like this. And as time goes on, the velocity is increasing. And so what that means is that for every subsequent point that I have here, I have a larger and larger velocity. So I have something that looks like this. Okay? So we can see, again, now that we drew this, we can look at this and say, does it correspond with our expectations? So if I look at this point right here, right? So let's say this is some time t is equal to 1. This has some slope like this, and that slope corresponds to the value of the velocity here at the same time. So this is time t is equal to 1. I could look at some later time, call this t is equal to 2. We can even write this in terms of seconds. So this is 1 second, 2 seconds. So here I have a larger slope, and what that means is I have to have a larger value of the velocity. So this is t is equal to 2 seconds. Okay? Are we on board with this? Okay, good, good. Okay. So now we want to do something a little bit different. So this problem says a train car moves along a long straight line. The graph shows the position as a function of time for this train. The graph shows that the train is speeding up all the time, slowing down all the time, speeding up part of the time and slowing down part of the time. We're moving at some constant velocity. So go ahead and talk about this one, and then we'll talk about it afterwards. No, it's fine. I think people would prefer it's a little bit too loud, not you're going to, you know.
They put in the request that we turn it on within the next hour.
Is it this whole building, or is it just this room?
It's just this room, I think.
Yeah.
Because I went in other rooms and they're like freaks in.
So what we need to do need to block their vents. I don't know, do I? I don't know. We need to block their vents to divert all of their air into this room, yeah. Okay, so what are we thinking, guys? What are we thinking? Uh-huh. 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 So, if we were going to plot what the slope looked like for different times, right? How would this look? Well, let's assume that this has some constant acceleration. So, if that's the case, if this is the case that it's a constant acceleration, then if we plot what the slope is as a function of time, where's the slope the largest? Earlier, right? At the beginning. As time goes on, the slope's getting smaller. So what does that say about the velocity? What's the velocity doing? It starts with a high value, right? Because the slope is large, and then it's decreasing as time goes on. Okay. And if this plot continued, this would kind of turn over, and eventually this would have a slope of 0, right? So at the top, it almost looks like it's getting very close to having a slope of 0, which means that the velocity would be 0, right? So if the velocity is 0, it stops. Okay? Does that kind of make sense? Yeah. Okay, good. Yeah, right. And then the question is, where would this, so let's talk about this one. So let's draw our plot here and let's see what's going to happen. Okay? So I have our position versus time on the left, or on your left, my right. So I have the position versus time here, and I want to draw what the velocity versus time looks like. And if we can draw what the velocity versus time looks like, we'll be able to answer this question no problem, right? So if I want to draw this, what I need to do is I need to figure out what the slope looks like here, and then plot that. So is this a large slope or a small slope, comparatively speaking? It's a large slope, right? So we start with a large slope. That means I start with a large velocity, right? And as time goes on, the slope is getting smaller and smaller until it looks like it's going to go to 0. So this is what my velocity versus time looks like. The point where it actually gets to 0 is a little bit past the edge of this plot. So what does that tell us? Well, it certainly tells us it's not speeding up, right? Because the velocity is getting smaller and smaller. So slowing down seems to be the case, but let's read the rest of them. So speed up part of the time and slows down part of the time. That doesn't seem to make sense with the plot that we drew here. And moving at constant velocity, this velocity is always changing. So it couldn't be that either. So the answer should be B. All right, so let's look at the next one. Why is this duplicating my questions? Okay, it's fine. All right. So now, let's consider this question. A train moves along a straight track, and its position versus time looks like this. Which graph best depicts the train's velocity versus time? Okay? So give that a couple of minutes to take a look at. Okay, so I think we're getting pretty good at these. So let's talk about this one. So this one, in a way, is actually kind of similar to the last one, right? We just add an extra piece to it. So this is what our position versus time looks like. It could be a little bit more parabolic. So more like that. Okay. So position versus time looks like this. We want to see what the velocity versus time looks like. So again, what we can do is we can pick a point over here and kind of ask ourselves what the slope is as we move from left to right along the t-axis. And so here I start with a large slope. Here, so I have a large positive slope. And then as time goes on, the slope is getting flatter and flatter until it goes to 0. okay? So that's the first part. And then when I get to a point where the slope is 0, it gets negative. So it goes like this. Okay? And so that's what our velocity versus time plot looks like. So can you describe to me, or somebody describe to me in words, what this looks like in terms of the motion? So if I was to describe this motion, if I had like, you know, my hands and I wanted to say like what's happening with them, what would this look like? Like a roller coaster? Well, if this was x versus y, right? Then yeah, it kind of looks like going over the hill of a roller coaster. But this is actually something that's just flat. This is something that's just moving in one dimension. Yeah.
Will it be something like coming to a stop and then going ahead?
Exactly. Exactly. It's going to be something that's moving this way and then it comes to a stop and then it moves backwards, right? And we can see that because it has some velocity going this way and then it changes direction and goes back, right? And it also, what we also see is that it starts with some initial position that's negative to begin with. So if this is 0, it's coming this way, with some initial velocity, it's coming this way, going this way, and then turning around. Okay? Good. Good. All right. So let's move on to the next one. Okay, so now here's a sample position versus time graph, this is a velocity versus time graph and acceleration versus time graph. And we want to see, is what the student said here, is this correct? So does this acceleration versus time plot match the velocity versus time plot? So take a couple of minutes to talk about this one. So let's talk about this one. So this one's a little bit different than some of the ones that we've had before because we're comparing the velocity and the acceleration graph instead of the position and velocity graph. But the relationship between the velocity and the acceleration is actually the same relationship that we have between the position and the velocity, right? Because they're just ratios of changes to change in time, okay? So when we look at this and we want to check to see, is my acceleration plot consistent with my velocity plot, we can just go step by step and look at what the slope is for our velocity plot and see if that corresponds to what we believe it should be for our acceleration plot. So when we're beginning this velocity plot, we have initially some velocity that's 0, right? So we have 0 velocity, that means it's not changing, and so if it's not changing, then the acceleration should be 0 as well, right? So we have 0 acceleration. And then we get to this point here, and we have some positive slope for the acceleration. So that means that if I have a positive slope for the acceleration, then I should have a positive value in the acceleration versus time plot, okay? Then we can look at the next one. Next one, it's flat. So if it's flat, that means there's no change in velocity. That means that the acceleration is 0. So we're 0 again, okay? Now we're getting to this portion right here. So for this portion, I have a negative slope, which means that the value in the acceleration versus time plot should be negative, right? And so this one should actually be negative here, okay? Now how about this part? So I'm looking at this. Is this a positive or a negative slope? Negative. Negative slope. That means that when I look at the acceleration versus time plot, what should I see? Negative. It should be negative, right? Okay, that's good. How about this one? It's positive or negative slope? Positive slope. What should I see here? It should be positive. So that means that B and D should reverse directions. Okay? Okay, good, good. So let's look at the next one. All right, so now we want to choose the 2 graphs that best represent the following story. A commuter train is on its way to a city. It stops and picks up a few passengers on the way and then continues to the city. So pick the 2 plots that describe this situation the best. Okay, so let's talk about this one, and then we'll move on. So let's talk about what these two plots, or what pair of plots we want for this situation. So if I was to walk to model what this train looks like, so our story is that the train's coming and it stops to pick you up, and then it continues on so it can take you to work. So train's going to move, it's going to slow down, it's going to pick you up, and then it's going to accelerate off this way, right? And hopefully not run into a chair. So when we're looking at these plots to describe that situation, which plot is going to describe our position versus time? C. Why C?
Slowing down, then it's stopping, and then it's
Exactly. So this plot is telling me that my position is, it's going towards 0, but as it's going towards 0, it's slowing down, and then it's going to speed up again, okay? So which velocity versus time plot corresponds to that? Have some disagreement. So I heard some E's, I heard some D's, right? So let's eliminate F. It's not F, right? So let's talk our way through D and E. So D and E both start off the same way. They both start off with some large positive velocity, which is what corresponds to what's happening here, right? We have some large positive velocity. And that velocity is going to decrease until we get to 0, okay? Now this is where D and E differ. So D says, once I stop, I'm going to increase my velocity again in the same direction. E says, once I stop, I'm actually turning around, I'm going the other way, because the velocity is going to become negative, okay? So of those two, which one should it be? D. It should be D. Okay, good, good. Okay, so let's move on to the next one. All right, so now we have two plots, and these are kind of like the classic problems that people say are, you know, what makes physics hard. But we're going to learn about how to solve these problems. And these are problems where you have two different objects. So the classic problem is a train leaves Chicago traveling at n miles per hour towards Cincinnati. Another train leaves Cincinnati traveling at a different speed. Where are they going to hit? Right? So this plot actually kind of represents that same idea here, okay? So we want to try to extract some information from this plot, and so it says, the graph shows positions as a function of time for two trains running on parallel tracks, which is true. More than one may be true. At time TB, both trains have the same velocity. Both trains speed up all the time. Both trains have the same velocity at some time before TB. Somewhere on the graph, both trains have the same acceleration, and the trains pass each other at time TB. Okay, so go ahead and talk to each other about that one. Let's go ahead and talk about this one. See what we have. So, what were some of the options that we came up with here? There's more than one. So we're saying C. Why C?
Why not?
Why not indeed? Yeah. There's a reason why C is true. Does anybody want to offer the reason why C is true? Yeah. Give me a second, I can't hear you. Yeah, go ahead.
The initial velocity is the same for A and B for time before IG or IB.
So the initial velocity is not actually the same, right? Because the initial position is the same. They start at the same point, right? But the velocity of these two is the slope of the line, right? So the slope at 0 is different for A than it is for B. But you're kind of on the right track. You're on the right track, yeah.
B starts out with a higher velocity. But A eventually passes B slowing down, so at some point B has
Right. So B starts with a higher velocity than A does, but A has a constant velocity, and B is slowing down as time goes on. So there is some point, and it's hard for me to point to, I don't have my laser pointer today, where the slope that I have at A is the same that I have at the slope of B, because B is changing from having a large slope to a small slope over the interval where the slope of A lives, okay? So that one's true. What's another one that's true? E, why is E? Yeah, well, it's a position versus time graph, and these two pass each other at time tb because at this time they have exactly the same. All right, so let's look at the next one. Okay, so now we're getting into some more numerical problems. So we want to read off what the velocity is at time t is equal to 1 second if we have this position versus time plot. So go ahead and take a minute to look at this one. So let's go ahead and talk about this one. So we're really kind of doing exactly the same thing we have been doing, only now instead of just doing it qualitatively or doing it in terms of plots, we want to apply some numbers to these situations. And so this question asks, what is the velocity at time t is equal to 1 second? Well, when we're looking at the position versus time plot, how do I extract the velocity? How do I read a velocity off of this? What's the meaning of the velocity on the position versus time plot? There's a slope, right? So then the question is, what is the slope at the point t is equal to 1 second? It's 2. Is it positive 2 or negative 2? Positive 2. Because we can look at this and it's increasing, right? And if we did the calculation explicitly, what we could do is we could say, okay, well, the change in the position divided by the change in time is going to give me the slope. So the change in position is going to be 2 minus 0, and the change in time is going to be 1 minus 0, and that gives me a ratio of positive quantities. Okay? Let's look at the next one. Okay, I don't want to do that problem. Okay, so now we want to actually get into doing some real calculations with these. And these are what are called the kinematic equations. The first two equations, actually, you can derive the third and fourth equation from the first two equations. And so that's what I want you guys to do now, is to show how can I obtain equation 3 and equation 4 by combining equation 1 and equation 2 in various ways. But we can see qualitatively, or we can talk about what equation 1 and equation 2 mean. So equation 1 says some final velocity is going to be equal to the initial velocity plus the acceleration times some time. So that kind of seems to make sense in a way, right? Because if I have some initial velocity, I start with this initial velocity, but I also have some acceleration that's going to change my velocity. And so if it's a positive acceleration, that's going to increase my velocity, and that increase in velocity is going to matter over some time interval, right? So we can say that the final velocity is equal to the initial velocity plus the acceleration times time. Similarly with the position, so if we say some change in position is going to be equal to the initial velocity times time. So think about position as, you know, I'm here or I'm here, and if I have some velocity, as time goes on, that's going to increase the distance that I move. But acceleration can also change the distance that I cover in position. And this term is a little less intuitive without calculus to explain exactly where it comes from, but the acceleration term in the position equation is going to be 1/2 at squared. Okay, but you can see dimensionally why that works out, because when we talk about position, velocity, and acceleration, the units of position are meters. The units of velocity are meters per second. The units of acceleration are meters per second squared. So it's a rate of change over rate of change in time. And so dimensionally, we can see why I need that t squared, because I want this entire equation to have units of meters. So if I have something that has units of meters divided by seconds squared, I need to multiply that by something with a second squared. The 1/2, again, I can't really get into exactly why that is without really delving into the calculus. Okay, so take a couple of minutes and try to figure out, how do I obtain equation 3 and how do I obtain equation 4 from equation 1 and 2? And the real trick to doing that is realizing what's missing from equation 3 or what's missing from equation 4 in terms of the variables that we have here. Okay, so go ahead and talk about that for, let's say, about 5 minutes. I don't want to spend too much time on it. So like I said, I don't want to spend too much time on this because this isn't quite the kind of question we'd ask you on an exam, but I think it is instructive to go through this to show where these equations come from, because you never really want to, I'm going to say this and I'm probably going to get myself into trouble. Don't trust me. Never trust me when I say things. You always want to question, when I say something's true, you want to know why it's true. And if I give you an equation, if I'm good at my job, I ought to be able to explain to you why it's true. And the way that I would explain to you why 3 and 4 are true to go through this derivation. So I'm going to go ahead and do this quickly for you guys. So starting with equation 1. So equation 1 says VF is equal to VI plus AT, and equation 2 says delta X is going to be equal to, let me make sure I write it the same way, delta X is equal to VI T plus 1/2 AT squared. Okay, so if I take equation 1 and solve for time, what I end up seeing is this is VF minus VI divided by A is equal to T, right? I move this over to this side, divide both sides by A, and I have this. So now what I want to do is I want to take this take this time and plug it into this equation. So what I have is delta X is equal to VI times VF minus VI divided by A plus 1/2 A times VF minus VI divided by A, and both of these are squared. So when I square this, this is squared, this is squared. I'm going to cancel a factor of A here, so I have a factor of A in the denominator. Then I can expand this. So this is going to be, this term right here is going to be 1/2 or 1 over 2A times VF squared minus 2 VI VF plus VI squared. And this term over here, sorry, this is going to be plus. Let me kind of rearrange it so it looks a little bit similar to this. This is going to be 1 over A times VF VI minus VI squared divided by A. Okay? So now when we look at this, this is, sorry, I moved my A out already. So now when we look at this term and this term are going to cancel each other, because this is just VF VI over A. This is minus 2 VF VI over 2A. These ones go away. Okay? Sorry, not the whole thing, but just this one and this one. Okay? Then what I have is a minus VI squared over A plus VF squared over 2A plus VI squared over 2A. So really, this right here is the same thing as this, barring a factor of 2. So this is really like -1 plus 1/2. So that's going to give me -1/2. So this is going to be minus 1/2 VI over A plus VF. These are squared. So this is VI squared, VF squared over 2A. Common factor of 2A. So this is going to be able to move to the other side. Now don't forget we had this delta X on this side. So if I move this 2A to the other side, what I have is minus VI squared plus VF squared is going to be equal to 2A delta X. And then I can move this to the other side, and then this is VF squared is equal to VI squared plus 2A delta X. Okay? And now, when we look at this, this is exactly what we have for this equation here. Okay? Now, we can do the same thing for the fourth one by taking this equation and solving it for A and plugging it in here. Okay, so that's how we're going to get the fourth equation. I'm not going to go through that because we're a little bit short on time. I want to get a little bit farther before we finish up. So, another clicker question. To use these kinematic equations, you must have a constant acceleration. Is this true, false, or what does the last one say? Acceleration and kinematic equations are not related at all. So what do you guys think? So what did we say for this one? Do we think it's true? Do we think it's false? Do we think that acceleration is not related to the kinematic equations at all? Hopefully nobody said C, right? Because we've been talking about acceleration in the kinematic equations already, right? What do we say? It's true, right? And it does happen to be true. Unfortunately, I can't, I mean, I can prove it to you, but you need calculus to be able to show exactly why it's true. Okay. So, this next one. Okay. This is getting into how we format our answers and how we think about the way that we're going to solve a problem. And there's a process that you want to follow in order to do this. And we'll, I have time to do this on this first question. The first thing that you want to do is to draw some big diagram representing what's happening with the situation. After you do that, you can write what your knowns and unknowns are represented in the diagram. And you want to include the variable names so you know what the initial velocity is, what the final velocity is, what the position is, what the acceleration is. After that, you want to develop a conceptual plan where you write down relevant equations and principles. And in doing that, you're making a plan and then deciding on intermediate information that you need. After that, you want to implement the plan, and typically that means that you're going to be solving those equations for the things that you're looking for. And then the last thing you want to do is evaluate your answer. Does it make sense? Is it the right order of magnitude? If I'm throwing a ball across the room, I shouldn't get something that exceeds the speed of light, right? If the units aren't right, you want to do your dimensional analysis. You also know that something's wrong if your units don't match. And then you want to look at limiting cases. So you say, what happens if this velocity is very big or it's a very small velocity? How might that change the question? Okay. So in the last couple of minutes of class, what I'm going to do is I'm going to demonstrate this problem-solving technique in this problem, and then on Thursday we're going to be doing more problems like this one. So this problem says that you're pushing a stroller, and let me get a piece of chalk. So you're a person pushing a stroller from rest uniformly accelerates at a rate of 0.5 meters per second squared. What is the velocity of the stroller after it has traveled 4.75 meters? And so I'm really bad at drawing, so I'm just going to represent the stroller as a box. Okay. So we have our stroller here, and it starts from rest. So we're doing the first portion right now. We're drawing our picture. It starts from rest. So we could even put a person here, and then I don't know. You could have like a baby or something. That's a baby. Starts from rest, and then at some later time, it's going to be moving with some larger velocity here. And you've pushed it like this, okay? So we have our picture now. Now what we can do is we can write down some of the knowns and unknowns. So what's something that we know? We know the acceleration. So the acceleration is going to be the 0.5 meters per second squared, okay? What else do we know?
Initial velocity.
We know, we actually don't know the initial velocity. We know the distance it travels, right? So we know the distance it travels. Or do we know the initial velocity?
It starts from rest.
Oh, it starts from rest, right. So the initial velocity we know as well. So the initial velocity is 0 meters per second, okay? We know the distance that it travels, right? So we know this distance that it travels is going to be this 4.75 meters, okay? So now we have all of our knowns and unknowns. We've drawn our diagram and we've labeled it. Now we want to decide on an equation that we can use based on the things that we know and based on the things that we don't know. So of those 3 equations that I had before, or the 4 equations that we have before, looking at the things that we know here and the things that we don't know here, which equation should we pick? The third one. Why should we pick the third one? There's no time, right? We don't know anything about time. So what we want to do is we want to use an equation that doesn't require us to know something about time. So that means we want to use a third equation for this. So we've drawn our picture, wrote our knowns and unknowns, we've developed our plan and said we're going to use this equation here. plus 2a delta x. And now we're ready to evaluate this. So we know actually that the initial velocity is 0, so we can get rid of that. Final velocity is going to be equal to the square root of 2a delta x, right? There's a it's a minor step. It's the mathematicians would get mad at me if I said this is a minor step. What am I missing here? I'm missing something. I need plus minus, right? Because a positive or a negative number can be squared to give you a positive number in the end. So you need a positive plus minus here. But for us, we can say, well, we're just moving in this direction, right? So we're going to choose the positive answer. And so now what we can do, we have the equation that we started with. We've done some algebraic manipulation to get it to this point. We can plug in the values that we have for our acceleration, our change in position, and our initial velocity we already got rid of. And what we see is this gives us an answer of 2.18 meters per second. Okay? So we're going to pick up with this again next time. We're going to do more problems like this on Thursday. So everybody have a good day.